Hi everyone. In this video, let's solve the question LeetCode 15 threesome. And the question states that given an integer array nums, return all the triplets nums of I, nums of j, nums of k, such that each of those ijk are not equal to each other, and they should all add up to 0. And the most important part of this question is that none of the triplets in the solution set should be duplicates. So let us begin. I'll take up the example which is given in the problem statement. So nums would be minus 1, 0, 1, 2, minus 1, minus 4. Let me write it here. Minus 1, 0, 1, 2, minus 1, minus 4. So our target would be to find triplets. So ni, nj, then k, such that they sum to 0. So coming to the brute force method, it's really straightforward. So essentially what we do is keep three pointers. The the first pointer is here, second pointer is here, and the third pointer is here. So if we do this, then for every I, we need to iterate through all the elements in the array and check the sum of the triplets. So first we'll have to check the sum of these three, and then we'll have to move this k forward, check the sum of 1 plus 0, and then this k, then move this k forward again here. So then now we check the sum of these two, 1 and 0, along with this k, and so on. And then in the in the first nested loop, we again keep running this j forward. So we move this j ahead. So now we check the sum of minus 1, 1, and then the k value, which would be j plus 1, which is 2, and so on and so forth. So after we complete both the inner loops for j and k, we would move I forward as well and keep continuing. So in this case, if you would observe, there'd be one loop running from I, the inner loop would be running from j, and then we would have another loop running from k. Okay, so I won't go much into the details of what we initialize as ij and k, but in essence we have three loops, and in the worst case the time complexity would be of n cube, which is certainly not too good for interviews. So let us try a better approach, and let me just copy the array again. So the idea here is to get three elements such that they add up to 0. What we can do first is we can keep this first element fixed, and then we can just apply to some technique that we learned in a previous video to find if the sum of all the three is equal to 0. But it's not your regular two-sum. So let us check how we can apply two-sum here. So if we have I here, right? So now let's keep I plus j plus k is equal to 0. If I is equal to minus 1, what should be the value of j plus k so that they add up to 0. So if you apply basic high school math, j plus k should be equal to 1, right? So because this should be equal to 0. So in essence, our target for twosome to find jk would be minus of nums of I. I hope this is clear. But this approach has a catch. So let me just explain what's the catch. So the process is really simple. So we keep I constant, and then from I plus 1 until the end, we initialize j and k here, and then we keep checking whether the sum of these two, is equal to minus of nums of I or not. And then, basically we keep moving it inside until they cross paths, until they reach each other. But the catch here is that, like we saw in twosome, we would have some space complexity, or we would need some extra space to store the hash map, okay, which basically keeps track of the previous element plus its index. So if you don't know about the twosome problem, or you don't have an idea of why we use a hash map, I will add a video in the description that you can watch and learn the twosome problem before jumping into the solution for this one. So this space complexity is a bottleneck. So what we can do now is I'll show you the most optimized approach that we can follow. Okay. So this optimized approach is very similar to the twosome 2 problem, which is the same as twosome, but the input array what we're given is sorted. So here the input array is not sorted, but first let us sort it, and then I'll show you how we can move ahead. So minus 1 0 1 2, minus 1 minus 4. Okay, so let me sort it first. So we would have a minus 4 minus 1 minus 1 again, 0 1 and 2. Now what it allows us to do is basically leverage sorting to make sure that we have no duplicates. So if I keep I here, and now I need to find my j plus k, which would have to be the negative of minus 4, that is equal to 4. So I need to find j and k here so that the target is equal to 4. So I'll keep my j here and I'll keep my k here, and similar to how we did in twosome 2, we will we will first add up j and k. So minus 1 plus 2, that is equal to 1. So this one is less than our target. So we need to increase our sum of j and k. And to increase it, we will move this j forward. So now, as you can see, we have a repetition here, right? So this j value is equal to the previous value of j, which is minus 1. So in order to avoid any duplicate pairs of j and k, we skip this and then we move ahead. Sorry. Okay. We skip this and move ahead to this 0. So now 0 is not equal to its previous element minus 1, and thus we can find the sum. So 2 plus 0. Okay, before we find the sum, we'll also have to move this k ahead here, and this k is not equal to the previous value of k, which is 2. So we are fine. It's not a duplicate. So here we would essentially have, yeah. So here we would essentially have 0 plus 1, that is equal to 1, which is again less than 4. So now uh, in the next iteration, when we move j here, so we see that j and k, they actually come at the same position. So once they're on the verge of overlapping, we just come out of our while loop like we did in 2 sum 2. So in this case, we haven't found solution, or we haven't found a triplet, right? Okay, and I suppose there should be a minus 1 here. Yeah, so there should be a minus 1. That was a mistake, but still we don't end up finding two numbers that equal to 4. Okay, now the next thing we have to do is again take the same array minus 4, minus 1, minus 1, 0, 1, 2. Now we are going to move our I forward here, okay, and then start our traversal from here, from the next element. And here what we do again is we keep our j here, our k here, and in this case our target would be, so would be I plus j plus k should be equal to 0. I is minus 1 plus j plus k equal to 0. So j plus k should be equal to 1, which would be our target. So now you can see that indeed in this case j plus k is equal to minus 1 plus 2, that is equal to 1, which matches our target. So we have indeed found our first triplet. So we add it to our res dot append. So it would be minus 1 and 2. This would be our first triplet value, and then in the next iteration we actually have to avoid the same ith element, and this is a really important step. So our I comes here, right? So until now we had checked if j and k had any duplicate elements or not, but we have not checked for I, right? So even I should not be a duplicate, because if we end up keeping I here, and we again we have the possibility of finding the same triplet values. So in this case we should not keep I mean we should keep moving ahead I, but before that there's a small optimization that you can do. So instead of moving I right now itself, right, so let us do one thing. Let us keep going here itself, right? Why don't we keep moving j and k forward and backward if we have a possibility of finding another triplet or not? So let me just continue the loop. 0, 1, 2. So this should be our I. Okay, and then so j and k were initially here. So now since we have found a triplet, we move this here. We move j inwards, and then we move k also inwards. So now again, right, if you can observe carefully, we have -1 plus -1 plus 1. Okay, so our target value here was 1. So in this case, you would have -1 plus 0, that is equal to -1. So we still don't find a triplet in this case. And now what we do is we move like I mentioned earlier. So inch 2 to avoid the duplicates, right? So instead of moving I from here to here, we just move I one step forward and we move it over here. So now if I redraw, 0, 1, 2. So I just skip this iteration, but I mean in the next step what would happen is they would, j would come here. Okay, and then j and k would be at the same index, so both they collide, and then we come out of the loop. So now we skip this and then we move I here. Okay, so now this is our window. So this is j, this is k. Okay, I just noted a small typo when I was just iterating through again, and this is something I would have to avoid in interviews. So here, uh, when you have a j and k here, right? So j is here and k is here. Now just clear all this out. Yep. So when I have j here, k here, in the previous iteration we added here. So now when we move this forward, j comes here and k comes here, right? So I took j as -1, but j here is actually 0. So this 0 plus 1 makes it 1, which is equal to our target. So -1 plus 1 is equal to 0, and we again get a triplet set which adds up to 0, right? So we append it again. This one would be -1, 0, and 1. So this is a thing that I missed out. I'm sorry about that. So in the next iteration, like I mentioned, we move I forward again, and in this case I is not equal to I minus 1, so we are good. And then j would start from I plus 1, and now j plus k is equal to 2 plus 1, that is equal to 3, and our I value is equal to 0. So I plus j, so this 3 is not equal to our intended target, which was in this case it would be 0, since we have a 0 right over here. So our intended target for j plus k should be 0, but this is 3 that's greater than 0. So now even when we move this j forward, you can see that j and k collide. So j is no longer, yeah, j is no longer less than k. So we just come out of that while loop, and now I plus j plus k is equal to 0 plus 2 plus 1, which is not equal to intended target of 0. So in like this basically continues until we reach length of nums minus 2. Okay, now why? Okay, why is the question here? So if you can observe, right, so basically our I continues until we reach length of nums minus 2, because here we reach length of nums minus 2. Or let me just take it in a separate space. Here we reached I is length of nums minus 2. So when we move here, when we move I here, what would basically happen is we we would need to have at least two elements to the right of I to be able to form a triplet, right? So it doesn't really make sense to move I forward, and we would end up in array index out of bounds error. Bounds, because like it wouldn't even uh, yeah, there either you end up with array index out of bounds if you code it one way, or if you code it using for loop, or it does not enter the j less than k while loop, because the reason is simple. So both j and k will be here itself, right? It will be on it will be on uh, 2. So in that case j would not be less than k, and we just come out of the while loop, so there's no point checking that. And that's the reason why we just move I until length of nums minus 2. So this was the explanation. Let us quickly go to the code. Okay, so in the code, the base case that we keep here is if length of nums is less than 3, then there's no way we would find a triplet, right? So we just return an empty array, and then we keep a result list here. Then we sort nums, and like I mentioned, we move this n or I pointer until length of nums minus 2. And if n not equal to 0, which means if you are not at the first index, and if the number at the nth index is equal to the number at the previous number, then we keep continuing, because we will end up getting duplicate triplets otherwise. And then we call the twosome with the nums array and one index more than I, pass in the result, and the target would be minus nums of n, like I showed you in the explanation. And when we call twosome here, I and j will be equal to k. So k is the n plus or n plus 1th index, and we pass in the result and the target. So the j index would always would always be at length of nums minus 1, regardless of the iteration that we're doing. And while this I and j, while I is less than j, so I mean, just to clear up, right? So in this case, what I had explained is I maps to n in the code, and j maps to I, k maps to j. So I just have an habit of writing. I just have a habit of writing for n in nums. So in the code. So this is what I am mapping it in the code, and you don't have to be confused. So while I is less than j, so this is the normal 2 sum 2 code. So if they're within the target, then we move j inwards. If they're less than the target, we move I inwards. And if we actually find that they're equal to the target, then we just append it to the result, and we do our normal I plus is equal I plus 1 and j is equal to j minus 1. And then this is a really important place where we check the duplicates for I and j. So if still I is less than j and nums of I is not equal to the previous nums of I minus 1, then we move I forward, because there's no point of checking the duplicate nums of I. Similarly for j as well. So we do this for length of nums minus 2 elements, length of nums minus 2 times, and therefore the entire time complexity of this would be big of n, the worst case. And finally, after the whole computation, we return result. So I hope it's clear now why we do the sort. Why we don't use the three loops. Why we do the sort. Why what happens when we do try this method when we have not sorted, and what happens when we have sorted. So this was all for the video, and I'll see you in the next one.